Seems to be an appropriate amount of silence, so I guess we can begin. That happened on its own. I'm Jim Sallee. I'm a professor at the Harris School of Public Policy Studies across the Midway here, and it's my pleasure to welcome you to tonight's events and to introduce our esteemed speakers, and later to help moderate the question and answer period. So what we're all gathered here tonight for is the current installment of the Center for International Studies Global Energy Series. Tonight the title of the program is From Field to Fuel, the Economics of Biofuel Energy. And we're going to be hear from Colin Carter and Madhu Khanna, both experts in the field. Before proceeding, I want to plug these upcoming events, which you can also see on screen here. So the next event is going to be with Seth Snyder, also an expert on biofuel technologies, who will be joining us from nearby down at Argonne National Laboratory. And as you can see, there's also a great lineup of talks that will be taking place in the spring. You can check out globalenergies.uchicago.edu for more information. This evening, we're going to hear from Colin and Madhu. And so I'm going to say just a brief bit, a very short introduction for each of them, and then turn over the microphone. Colin Carter is the Distinguished Professor of Agricultural and Resource Economics at the University of California at Davis, and he's the Director of the University of California's Giannini Foundation of Agricultural Economics. Colin's from Alberta, so if you have any questions about tar sand or the Keystone Pipeline, he might be a good person to ask. Colin received his Ph.D. In agricultural economics from Berkeley, and has since then published in a wide variety of topics ranging from trade, agricultural policy, a lot of work on futures and commodity markets, and as they relate to the agricultural market, and has a recent and ongoing research agenda on China and agriculture there, and he has won a number of teaching and professional awards and recognitions, and was recently named a Fellow of the American Agricultural Economics Association in recognition of all these contributions. Tonight he's going to give a talk titled The Unintended Consequences of Mandated Use of Food for Fuel. After Colin goes, we're going to have Madhu Khanna speak. She comes from a little bit nearby, down at the University of Illinois at Champaign-Urbana, where she's a professor in the Department of Agriculture and Consumer Economics. She also got her PhD from the University of California at Berkeley, and has written a breathtaking number of articles on areas ranging from in the areas of environmental economics, and has recently, or actually I don't know if this is recently, has co-edited a book called The Handbook of Bioenergy Economics and Policy, and has also received a variety of awards and recognitions. She's currently editor of one of the most important journals in the area, the American Journal of Agricultural Economics, and I could go on listing their accomplishments and qualifications, but I'll let them do the convincing. And I trust that you guys will give them the Chicago treatment of asking them difficult questions and not respecting their authority when it's your turn. Madhu is going to speak tonight on these issues. Her talk is going to be titled Risks and Returns from Energy Crop Production in Rain-Fed United States. So we're going to hear first from Colin and then Madhu, but please join me now in welcoming both of our speakers.
Good afternoon. Thank you very much, Jim, and thank you, Andy, for the kind invitation. It's a pleasure to be here. So I'm going to speak mostly about corn ethanol, and Madhu will speak about more advanced biofuels. So that's more or less how we've divvied it up. So Jim mentioned that I will talk about the unintended consequences of our corn ethanol policy. And my focus primarily is on the impact on the price of retail gasoline. And I think this is a topic that is not discussed thoroughly enough. So first of all, in 2007, the U.S. government ramped up its targets for renewable fuels significantly, and that's the current policy that we're operating under. The policy has a target of 36 billion gallons of renewable fuels by 2022. We're not even halfway there yet. We're around 15 or 16. Between now and 2022, which isn't too far away, this policy calls for an annual increase in the volume of biofuels that are blended in with our gasoline. Now, one of my claims this evening is that these annual targets and the increases that we're looking at every year are really based on outdated assumptions which are no longer correct. For example, the policy was implemented at a time when the U.S. Environmental Protection Agency expected gasoline consumption in the U.S. to increase, but actually it's decreasing. It's gone down about 6% over the last 5 or 6 years. And also, Madhu will talk about the second generation biofuels. The policy is predicated on the availability of these fuels, but they're not yet there. This is making the EPA's job very difficult, and this whole issue has actually been drug into the courts recently. So this year, the target is just over 18 billion gallons of renewable fuels. And that includes some what we call advanced biofuels. Advanced biofuels basically indicate that they are truly low-carbon fuels. So these are cellulosic fuels, 2 billion gallons. Madhu is going to talk about those. And biodiesel, roughly the same. And then if we remove those advanced biofuels from the overall target, what we're left with is the implied target for corn ethanol, which is considered conventional biofuel. And there's a lot of controversy about this, but the bottom line is that corn ethanol is not even really considered to be a low-carbon fuel anymore. But our target this year is to use 14 billion gallons, which is more than 10% of our gasoline consumption. So that's the long and short of the policy and where it's taking us in the future. Those in favor of this policy, which do not include myself, argue that these targets have lowered U.S. dependence on imported oil, they've lowered the retail price of gasoline, and they've lowered CO2 emissions. This graph shows the uptake in the use of corn ethanol, and you can see that one reason this issue is getting so much attention is that we've used a massive amount of our corn supply to put in our automobiles, and just over the last 5 or 6 years, the volume has increased 5 or 6-fold. The theme of my talk is sort of a political economy theme, because we're actually at a very interesting stage, this week and next week, with regard to the ethanol scheme. And I'm arguing that the public and some aspects of the government may be turning against corn ethanol, and this is a relatively new development, but not particularly surprising. When you look at the price of food, that's increased more than any other item in the U.S. CPI. It's up about 21% since 2006. And it's really no wonder, because right now we're using 34 million acres of corn and 11 million acres of soybeans for biofuels in the United States. In total, that's about 50% of the cropland in the Corn Belt is used for fuel. And we're not even halfway towards meeting our target. So taking these crops, soybeans and corn, off the market has driven up the price of food globally. This all came to head in 2012 when we had a massive drought that you probably remember. Corn yields were down close to 30%. Actually, the loss in the corn crop that year was almost identical to the amount of corn that we used for ethanol. So it was a big drop in production. And this drove up corn prices dramatically, up threefold in other competing crops. And there was an appeal made by a number of governors to the US EPA to temporarily reduce these targets that it sets. Essentially, they set quotas for how much corn ethanol must be blended in with the gasoline. And the EPA had a comment period. I was involved in that, and I'll talk about that in a second. In the end, they denied the request. In other words, they left the targets in place, and instead of using that food for food, we used it for fuel, and we kept producing fuel with it. And the EPA determined that if they had waived the request, it would have had a very negligible impact on the demand for corn and corn prices. In other words, what they concluded was that the industry would continue to demand corn for ethanol even if the mandate was removed, which I find kind of interesting. Another reason that the public is getting skeptical of corn ethanol, there have been a number of reports like the one from the National Academy of Sciences that basically concluded that corn is not a low-carbon fuel. In California, where I live, we have a California Air Resources Board, and they struggle with this, and basically they're of the opinion that it's not a low-carbon fuel. The only reason that it meets the EPA targets for being a renewable fuel, and for this particular fuel, it's a 20% reduction in greenhouse gases, is that virtually every ethanol plant in the US has a waiver that's grandfathered in, so they don't have to even meet the 20%. So that's, the public is slowly catching on to this. So 2012, we had the drought. 2013, we're seeing consumption of gasoline coming down, and we're seeing quotas for ethanol use going up. So one's coming south and one's going north. And we hit the blend wall last year. What does that mean? That means that once we got to about a 10% blend, and it's not quite 10, it's something like 9.6, gas prices started to increase. Gas prices at the pump, and that's my focus tonight. Because there's difficulty in blending more than the 10%, and if the EPA is saying you must blend more than 10%, but it's virtually impossible to do that because the warranties on most cars are invalid if you go above a 10% blend. We have flex fuel vehicles that will burn E85, but nobody buys E85 because it's too expensive. So it's just very difficult to increase past that 10%. So as a result of this, it was sort of, for the first time ever, the EPA indicated that maybe there's a problem with our corn policy. They denied it during the drought, and they sort of skated through that drought period. But now they realize, this is starting to impact gasoline prices. So a few months ago, in November, the EPA came out and they said, well, for 2014, we might lower that target slightly. And this is why I say it's very timely, because the announcement has not been made. They've had a comment period. Thousands of comments have been submitted by these various groups. And they were proposing that they reduce the target for 2014 from 14.4 to 13 billion gallons of corn ethanol, and there was also some adjustments on the advanced biofuels. So this was reducing it back to about 2012 levels. Not a huge decrease, but at least a suggestion that maybe the policy is broken. One reason that the EPA made this proposal is that I think the White House started to become concerned about the impact of this program on gasoline prices. This graph shows the price of blending credits. It's a little bit complicated. They're called RINs, that's the acronym. And basically, if you have an obligation to blend ethanol or biofuels into gasoline, and that would be if you're, say, a refiner or you're an importer, you have an obligation to blend, let's say 10%. Well, if you're unable to actually do the blending because you can't sell the blended product, you can buy one of these credits in the market. And so the price of these credits went from, a few cents a gallon to $1.40. And so you can imagine if you're making motor fuel and you're putting in 90% gasoline and 10% ethanol, and you can't add the 10%, you have to buy a credit instead. Well, that adds to the cost of the product you're making. So the long and short of it is that these high RIN prices started to be reflected in gasoline prices. Then the story is that the industry got wind of the fact that the EPA was considering moving back from the blend wall, and the price of RINs crashed. Now, the last few weeks, the price of RINs is going back up to 60 cents a gallon, and the suggestion is that the EPA may back away from their proposal because they're being threatened by lawsuits from the industry, and there's all this opposition from these very powerful groups, the corn farmers and the renewable fuels industry, that they shouldn't tamper with the policy, and if they do, they're going to end up in court. So these are the numbers that I'm studying. And so I'm looking at, okay, what impact does this policy have on the price of motor fuel? And so when you look at the price of ethanol versus gasoline, that's shown in this graph, you see that the ratio over time is around 0.9. Ethanol is a little bit cheaper than gasoline, but in fact it should be quite a bit cheaper because it has 1/3 less energy. So in other words, if you put a gallon of ethanol in your car, you're only going to drive 2/3 of the distance if you put a gallon of gasoline in your car. So based on energy, that ratio should be around 0.7, but it's higher than that, which means that ethanol is more expensive than gasoline when you adjust for the energy content. Interestingly enough, when you look at Brazil, where consumers have a choice at the pump, that ratio is about 0.7. In other words, ethanol in Brazil reflects its energy content. Okay? Also in Canada, Jim mentioned I'm Canadian. You pull into the pump in Canada and you have a choice. You can buy gasoline blended with ethanol, or you can buy gasoline that's good old-fashioned gasoline. In the US, we don't have a choice. And I think that's why we're seeing this price of ethanol being overpriced. And the long and short of it is, because of the mandate, consumers have no choice. The refiners and the blenders can add ethanol into the blend and not lower the blended price. In other words, they're cutting gasoline with ethanol, and as consumers, we're paying a higher price for an inferior fuel. Another way of saying this is that retail fuel is priced on a volumetric basis. It's just so much per gallon, irrespective of the energy content. And some of my research has found this. Why are we pricing it volumetrically? You might think, well, isn't the market competitive where, if you don't price it, if you price it volumetrically, the guy across the street is going to offer it for a lower price? Well, no, because the consumers don't have a choice. And we're not dealing with a perfectly competitive industry when we talk about the oil industry and the refiners. So one reason that the industry initially loved ethanol is because they could cut it into gasoline and not lower the price. And it's kind of circular reasoning that the fact that there is volumetric pricing, I think, is driven by the fact that it's mandatory. So when the drought happened, I mentioned we submitted this long comment to the EPA, and we argued that a waiver would have an impact if the finished gasoline was priced according to energy content. In other words, then the oil companies would probably buy less ethanol. And the EPA came back and said, well, okay, that's interesting, but we don't see any evidence that changes our assumption as to how ethanol is priced. In other words, the EPA basically concluded that ethanol blended into gasoline is priced volumetrically. And I think that's a significant issue. According to our research in 2013, this policy added about 15 cents a gallon to retail gasoline. Roughly 10 cents of that was due to blending in an inferior product. Those rents are shared by the ethanol industry, the corn farmers get some, and the oil companies get some, and it costs U.S. motorists about $20 billion a year. I think going forward, unless this policy is changed or somebody tomorrow discovers a way to convert algae into advanced biofuel, that these RIN prices are going to continue to increase as we force more than 10% into the blend. If we force more than 10% into the blend, oil companies are going to start exporting gasoline, they're going to export diesel, because if you export it, you don't have to blend it. If you sell it domestically, you have to blend it. And how can they blend more than 10%? It's very, very difficult to blend more than 10%. So that's going to send the price of gasoline higher. So I think unless the policy is changed, there's a strong likelihood we'll see a big spike in gasoline prices in the next year or two. Now, interestingly, the ethanol backers are fighting this EPA proposal. As I said, there's now a rumor, and it seems to be showing up in the price of RINs, that EPA is going to backtrack. So, you know, the president of the Renewable Fuels Association has come out very strong, saying, if you modify the policy, you know, we'll see you in court. So, I guess my conclusion, ironically, the EPA's write-down, in other words, if the EPA goes ahead with their proposal, it could actually save the ethanol scheme, because it's not going to draw the attention to this scheme that you would see if gasoline prices went up 50 cents a gallon. But yet the ethanol backers are fighting it. And I think the EPA actually has a method to perhaps save the whole scheme, but now they're being scared off by the very industry that would go down with it. Thanks, Jim.
Well, good evening. Thanks for the invitation. It's a great pleasure to be here and to share some of the research that we've been doing. This is work that's being done, you know, in conjunction with the Energy Biosciences Institute that was formed about 5 years ago with significant funding from BP and in partnership with Berkeley. So just picking up where Colin sort of left off, the policy that you know really stimulated this interest in biofuels was the Energy you know, Independence and Security Act of 2007 that mandated that we should have 36 billion gallons of biofuels blended annually in our transportation with transportation fuel by 2022. And recognizing that you know, we could not rely only on food-based biofuels like corn ethanol because of its implications for food and so on, they mandated that at least 16 billion gallons out of that needs to come from, be in the form of these advanced biofuels that would be produced from cellulosic materials. And so today what I want to talk about are some of the, you know, the potential for these cellulosic biofuels and what some of the constraints are and what needs to happen in order, you know, to make them more of a reality. And so there are various sources of feedstocks for these cellulosic biofuels. Essentially what is required is biomass that could come from a variety of different sources like crop and forest residues, short rotation woody crops like poplar and willow and so on. But one particularly promising source is these dedicated energy crops. And again, there are many types of these energy crops. Native prairie grasses is one example, but more higher yielding varieties of that would include things like switchgrass, miscanthus, which has been essentially experimented with considerably at the University of Illinois Energy Farms in Urbana-Champaign, energy cane, which is very promising, from the family of sugarcane, but very rich in biomass. And one of the characteristics of these crops is that they are perennials, and they can be grown without irrigation. So most of the effort has really been on the potential for growing them in the rain-fed eastern half of the U.S. They're relatively high yielding, as I'll show you in a moment, and they are typically, we're looking at non-invasive varieties, so not being sort of concerned about invasive problems. And more importantly, they can be actually grown on marginal, low-quality land. So they would not compete directly with food crops and would not have the kind of adverse consequences that we've seen with corn ethanol, because they would not be diverting land away from food production. They also have the potential to provide a number of environmental benefits, like the soil carbon sequestration. They are low carbon intensity in the process of producing them. They do not require the kind of fossil fuels that are needed to produce corn ethanol, because they themselves generate material that can be used to power the refineries, and you get energy from biological sources. They can reduce soil erosion because they have very deep root systems. They are perennials and therefore don't require to be tilled and don't require the kind of chemical inputs and so on that are typically needed for annual crops like corn and soybeans, and therefore can reduce leaching and nitrogen runoff. Although they do have a sort of a high requirement, because they're a grass, they do require considerable amounts of subsurface water, and so there can be some concern about their growing them in large areas, and what the implications of that might be for subsurface hydrology. Okay. So here's sort of an example of miscanthus. As you can see, a very productive grass. You plant it and it comes back. It takes about 2 years to get established, and then every year it grows to a height of about 14, 15 feet and generates this incredible amount of biomass without too much application of chemical inputs. On the right-hand side is and this is all from the energy farm in Illinois, in Urbana. Here are miscanthus growing next to switchgrass and corn stover crop residues, which can also be used. So just a little bit more on about the returns to farmers, or and why they would want to convert, or what the limitations might be that will prevent them from converting land and actually growing this type of crop. These crops have 10 to 15-year lifetimes. They do require considerable commitment from farmers who are typically used to growing annual crops and making a decision every year whether to how much of corn and how much of soybeans to plant. Now they'd have to make this long-term commitment. There are upfront investments required in planting and establishing these. And these crops need to yield enough of a return to farmers that would compensate them for giving up the return from their regular conventional crops, so it would have to cover that foregone return. It also sort of exposes farmers to various risks. So now they're producing something whose price is going to be linked to the price of a volatile energy, fossil energy source like oil. There are yield risks associated with it, just like with any other agricultural crop, but these might be different for these crops as opposed to conventional crops. There's a possibility that they could be a failure, and in which case they would lose their entire investment and have to start all over again. On the other hand, there might be some benefits because they can diversify into a new crop away from just the standard crops that they've been growing. And then finally, when they give up their land from corn and soybeans, then there is this possibility that if the price of corn goes up, then the value of their land, they've really given up a significant amount of income. So that that's also exposing them to risk in terms of what is the foregone value of their land that they are investing in this crop. There's also sort of risks from the demand side, because it exposes these farmers to, it would expose them to a limited number of biorefineries in that area, and there might be just a single refinery. This would have to be essentially like a plantation type of cultivation within a 30 to 50 mile radius, farmers supplying to a particular refinery, because these are very bulky to transport. So these are low density, high volume, and bulky biomass to transport. It's going to be costly to transport them long distances. So the fortunes of the farmers are going to be linked very much to the fortunes of a refinery. And if there's a refinery shutdown, there's sort of might be limited options for what to do with this energy crop. There's limited uses for it other than for energy purposes. And in large part, the refinery is going to be affected by policy incentives. And there's, as we've just seen, there's a lot of uncertainty about the policy itself. Whether the EPA is going to maintain those mandates or waive them is going to influence demand for biofuels, and therefore that's going to cause additional uncertainty about the benefits of producing these types of crops. So what I wanted to sort of do, really briefly, although this might be a bit of an ambitious agenda to go through this, but anyway, kind of talk a little bit about, what some of the issues related to the risks associated with energy crops and the possible benefits of growing them, how that's going to be affected by the preferences of the farmers and whether, their ability to bear those risks, and the kind of risk management tools that would need to be designed if we really want to induce conversion of land to the production of these types of energy crops, and the sort of policy instruments that would need to support that. So just to sort of give you a little more idea about what, some of the costs and the benefits of growing these types of grasses, we did a study looking at 3 potential locations. And again, because we don't currently have large-scale actual production of these crops, a lot of the work that's being done is basically using models that are calibrated with the data that's coming from these experimental plots for the type, like the ones that at the energy farm at Illinois, and that's being used to calibrate, biophysical models of crop growth and so on, and we link those to economic models to understand what the costs and benefits are. So here are 3 examples of, high productive land, moderately productive land, and then relatively less productive land from a corn perspective. And at those 3 locations, we look at what is the yield of these crops going to be, how does it compare to alternatives, and what are some of the costs and benefits. So just to sort of compare these, we can compare these to crop residues, such as you can use corn stover, grow that with corn soybean rotations, continuous corn, and so on. Compare that to switchgrass and then miscanthus, and here is corn ethanol. And these are at these 3 locations. And one of the things that you could sort of see is that as compared to corn ethanol, these grasses have the potential to produce much more biofuel, gallons per acre of land that would be diverted, and you can grow them fairly productively even on low quality land. So if you grow them on low quality land, there is some loss of yield relative to high quality land, but it's not a great deal. And it's still more productive than what we get currently from corn ethanol. And also that these grasses are much more high yielding than what we could get from corn stover. So corn stover yields are relatively low, and their potential to produce biofuels is also comparatively relatively low. So if you're really talking about trying to get to a 30% share of biofuels, and by say 2030 or so on, then we'd have to move away from just using crop residues to actually having dedicated energy crops. And so we then can do something called life cycle assessment and calculate what is the cost of producing these, what are the carbon emissions that go into the production process, and compare them across these different types of feedstocks. And essentially we can do that for gasoline. We can also do the same thing for any type of renewable fuel, look at every input that's going into it, the fertilizer, the gasoline, and so on, of getting it from the field and the farm to the gas station, and then calculate and compare those. So when we do that, again, for these different feedstocks at these various locations, we can kind of get a sense of the different elements of the cost and then what it costs finally in terms of what it might cost to deliver this fuel at a gas station. So one of the things to note here is this green bar. The green bar is really the cost of the feedstock itself. Per gallon or per liter of biofuel, what is the cost of the feedstock itself? And this yellow is the cost of converting it into fuel, and so at the refinery. And of course, you could sort of see that a big part of the cost and one of the major stumbling blocks right now is this cost of conversion. So this is a fairly optimistic cost that is not really even the cost today. But it's the expected cost once we do have a mature technology. And even then, that is really one of the biggest components of the cost. But in terms of the feedstock cost, it's, again, these sort of grasses have a relatively low feedstock cost of production, much lower than that of crop residues. And that's because of their high yields. And then this pink is the cost of the land. This is the income that's being foregone that they would need to be compensated for, which is not the case in the case of corn residues because it's a byproduct. But even after you include that and include all of these costs, these energy crops have the potential, particularly if grown on low-quality land, to give lower cost fuel than the crop residues. So, and the cost of gasoline, this is in liters per energy equivalent gasoline. The cost of gasoline, this is 2010 prices, is about 60 cents a liter. So you could sort of see that even the most optimistic case here is considerably more expensive than gasoline today in an energy equivalent basis. And so a major part of this is the cost of converting it. The technology is currently so expensive that we don't see that, and that's why you need to have mandates and other incentives in order for the production to take place. So anyway, the point here is that you can grow this thing productively on low quality land, and there is a considerable difference in the cost between producing it on low and high quality land. So something like switchgrass grown on high quality land would be much more expensive than miscanthus grown on low quality land. Looking at the potential to reduce greenhouse gas emissions. So here we're measuring greenhouse gas intensity, which is grams of carbon dioxide per unit of heat, a megajoule. The carbon intensity of gasoline is about 94 grams of CO2 per megajoule. The renewable fuel standard basically defines cellulosic biofuels as anything that, as biofuels that reduce carbon intensity by at least 60% relative to gasoline. So all of these fuels would meet that standard, but if we look at particularly these energy grasses, the carbon intensity, you add up the various components of soil carbon and all the rest of it. The green dots here tell us the final net carbon intensity of the delivered fuel, and you could see here that it is negative. So in fact, these grasses are likely to be sinks for carbon, not sources, because they have such a huge potential to sequester carbon in the soil. And also because they're above ground emissions, the emissions needed in the form of tractors and fertilizer and gasoline to power the tractor and so on is relatively small, including the emissions needed for converting it into fuel. And so overall, the benefit of these is that they could reduce emissions by more than 100% relative to gasoline. As opposed to that, if we're looking at crop residues, these are likely to be sources for emissions, although much better than gasoline, but a positive source because they have, they lead to a loss of soil carbon. So when you pick up this residue, you are actually depleting the soil of its soil organic matter, and so there is a loss of soil carbon because of which these crop residues are a net emitter. Okay. So we have, essentially, if we look at cost of ethanol here and we look at savings in terms of greenhouse gas emissions on the x-axis, we can see that some of these energy grasses can in fact lead to 130, 140% reduction or savings of carbon emissions relative to gasoline, and at a relatively lower cost than some of the crop residue or even some of the other feedstocks like switchgrass. The current policy, which is a renewable fuel standard, basically treats all of them identically. So all of these feedstocks which can reduce emissions by at least 60% are given a uniform treatment. They are qualified to meet the mandate, and the policy itself does not create any particular incentive to go for the more lower carbon type of fuel. And so one of the arguments one would make is that one needs to have policies which actually reward these types of lower carbon fuels, for example, like a low carbon fuel standard like the kind that is there in California. And so we can talk a little bit about that at the end. Okay. Just sort of going from those 3 locations to the entire rain-fed region, you can now map out and see what would the yield of these be. And we use sort of 30 years of weather data with this simulation model called DayCent to look at what the average yield would be across the entire rain-fed region. And we could sort of see that there are some regions that are better for producing these grasses than others. As opposed to corn, where the yields are much higher in the Midwestern US, the yields of these energy grasses would be much higher in the south and southeastern part of the US. So there seems to be a nice complementarity in that what we're likely to observe is actually a mix of these feedstocks. It won't be a single feedstock. We're more likely to see maybe corn stover being gathered and harvested in the Midwest, and these energy grasses being grown more in the south and the southeast. Now, in addition to looking at just the average, it's also important to look at the risks. What are the variabilities in the yields going to be from year to year? And the reason that's important is, of course, from a farmer's perspective, that matters because their income is going to be variable from year to year. And if you're going to be relying on this as a source of fuel, then it matters as well because our energy supply is going to be affected by droughts and weather events. And so if we compare the relative riskiness of miscanthus and switchgrass compared to corn, here's miscanthus and switchgrass. For these red colors, that implies that the miscanthus is more risky than corn, and the green colors imply it's less risky, and same thing for switchgrass. One of the things we can see is that in general, switchgrass appears to be more risky than corn, whereas miscanthus appears to be less risky than corn, although there are regions where, in fact, it is more risky as well. So that's going to affect the type of prices that a farmer might want in order to be induced to grow these crops. So if you have farmers who are risk averse, then they would need to be paid a risk premium in order to be induced to grow these crops. And so one of the things we can do is to analyze what that risk premium is going to be. And so when we do that across these different regions, we can see that, looking at what the prices might be, again, prices are relatively, this is dollars per ton of the biomass. They're relatively lower in the southeast and higher in the Midwest and in the plains. There is an increase in price, about 15% or so because of risk aversion. So we're really talking about, prices close to about $70 to $100, $115 a ton for this biomass. If it's grown on cropland, much lower prices, so $40 to $50, $60 if it's grown on marginal land. And so to the extent that farmers have low quality land which is currently not being used for crop production, the first incentive would be to produce these types of grasses on that land and not to divert cropland. So the economic incentives will play in the direction of using low quality marginal land first and cropland only if the prices are really high. Okay. So these prices, one can see how they differ across the region, and that's kind of the risk premium that would be needed. Much higher risk premium for growing it on cropland in the Midwest, particularly for switchgrass, because it's more risky, you need much higher prices than for miscanthus. But there would be regions here where, in fact, because it's less risky, farmers would be willing to grow this even with a negative risk premium because it's less risky than their other uses. So thinking a little bit about, do we have the kind of marginal land that is, how much of it is available? And so this is using data from the 2007 census by the USDA. And that's essentially what, the distribution of land in the US, the agricultural land in the US, or the non-urban land looks like. We've got about 123 million hectares in crop production. There's a category of permanent pasture land that's about 79 million hectares. And then there is this category here, which is in the rain-fed region, is only about 11 million hectares or so, which is in this category called cropland pasture, that is rotating in and out of crop production, and it could sort of fallow and active in some years. Now how much of that is actually usable is something that's still very much a subject of research. But just a back of the envelope calculations would suggest that if you had, if you could use all of it and get about 15 metric tons with a high yielding grass like miscanthus, you could produce about 13 billion gallons of biofuels. And that's obviously a considerable amount that could be produced potentially from the available land without going to cropland. Let me just sort of very briefly talk about some of the risk management strategies that would have to be developed, and because this break-even analysis is sort of assuming that farmers are going to bear the entire risk, but actually, of course, refineries and farmers are going to have to do this together because they're both dependent on each other for reasons mentioned before, and so there's going to be some sharing of risk. Farmers differ in their risk preferences, and some may be more risk-loving and willing to bear more risks as compared to other farmers. So what this is sort of essentially going to require is contract farming, which ensures that there is demand for the energy crops being produced by farmers, some supply supply for the refinery so that they have an assurance, sharing of those upfront investment costs, and also something to address the liquidity constraints for farmers who in the first 2 years would get no income while this crop is being established, and therefore, if they're credit constrained, that could be an issue that would prevent their willingness to grow this. And then finally, it requires possibly some, crop insurance. So our regular crops like corn and soybeans are covered by crop insurance. The latest Farm Bill provides a significant amount of subsidized crop insurance for farmers, and that'll make them reluctant to grow energy crops if they didn't have a similar tool to cover the downside risks of producing them. Let me sort of just maybe talk a little bit about other policy incentives that would be needed. The current Farm Bill provides some incentives in the form of there's a biomass crop assistance program that would provide cost share and other subsidies for biomass production. We talked about the renewable fuel standard and some of its limitations. California has a low carbon fuel standard that basically sets a greenhouse gas intensity target, and this kind of a policy would create more incentives for these low carbon fuels. The other alternative would be a possibility would be a carbon tax that would tax the high carbon fuels and provide and lead to sort of a tax credit for something that's going to be a negative carbon fuel. And these are going to affect the prices of these energy crops. It'll create more incentives to produce them, but at the same time will not address these risks and the price and yield risks for which one might need to have some kind of subsidized crop insurance moving forward. Just in the last couple of minutes, this is just to show how different policies can actually lead to very different mixes of these biofuels. So we looked at, what would be the mix of biofuels that would lead to the same greenhouse gas reduction as what the renewable fuel standard, if implemented in its full entirety of 36 billion gallons over this period of 2007 to 2030 look like. So if the RFS, if it were to be implemented as planned, it would basically 2/3 of it would still be corn ethanol over this entire period, despite the 16 billion gallons from cellulosic sources. And the share of cellulosic energy, from these energy crops would be only about 12%. As opposed to that, if we had a low carbon fuel standard, which just had the 8% reduction in greenhouse gas intensity as its target, the target in California is 10%. So even if this was at a national level, 8%, It would require about 70% of the total fuel mandate being met by cellulosic energy crops, and a much smaller share of corn ethanol. As opposed to that, a high enough carbon tax, I mean, $50 per ton, which is very high, much higher than what we've observed in Europe, where they do have a carbon market, would still not be enough to incentivize these energy grasses because of the high cost of producing them. And it would achieve the same reduction, not so much by inducing a switch from gasoline to biofuels, but really by cutting down the vehicle miles traveled. It would raise the price of gasoline and reduce the amount of miles traveled and try to achieve a reduction in greenhouse gas emissions through that route rather than by switching to an alternative fuel. So policy incentives can play a big role in the type of biofuels that are produced and the quantity of biofuels that would be produced. They'll also affect the region where you might see these different grasses grown. This is under the RFS. You'd have some energy grasses, a lot of crop residues. If you had a low carbon fuel standard, there'd be a lot more regions with energy crops being produced, less reliance on crop residues. Okay, just to end up, these energy crops, in addition to these issues related to incentives for farmers, create this benefit that they need this less smaller diversion of cropland, likely to have less adverse impacts on food prices, much greater potential to reach those high volumes of 36 billion gallons, possibility to actually lower and affect the world price of oil because the US is such a major consumer of oil in the world market. Okay? And so in conclusion, there is considerable potential if the technology were to develop that would allow for commercial production of cellulosic biofuels to meet a significant share of the transportation fuel without these adverse impacts on food prices, potentially a sustainable source with many environmental benefits. The incentives to grow them will differ spatially. There'll be a mix of different types of feedstocks, and they'll be grown in different regions. But what's needed in addition to the policies on the biofuel side is also policies to cover risks and induce farmers to be willing to convert their land to grow them. So I'll stop with that.
So I'll say thanks to both of our presenters, and then now's your opportunity to chime in and to hear from you. So if you have a question, just raise your hand. We're going to use the microphone. And so does anyone have a question or comment? There's one in the back there.
Yeah, could you talk about how cellulosic ethanol may or may not come up against a blend wall as well?
Cellulosic ethanol will not affect the blend wall. The blend wall is caused by the number of flex fuel cars that can actually consume higher level blends and availability of retail distributors to supply the E85 that could be used to fuel them. So the renewable fuel standard is really a supply side policy that didn't factor in the fact that the demand is going to be constrained by the availability of cars to consume the biofuel. So that's and that's one of the limitations, as we can see from these policies, that is causing a rollback of the mandate, is as much the lack of supply of cellulosics right now as the lack of demand to consume biofuels.
Hi, I just have a quick question. So, do you see any potential for the production of biofuels outside of the U.S., say in Asia or in South Asia?
Yeah, I'm putting my money on algae. China's investing heavily in technology associated with converting algae to fuel. This would be grown in the sea and also inland.
So outside of the U.S., really the biggest and the major producer of biofuels is Brazil. And Brazil was the largest producer until recently when the U.S. overtook it. Brazil currently uses only about 1% of its arable land for biofuel production, and they're able to meet 50% of their domestic supply of domestic demand for transportation fuel from sugarcane ethanol. They were also the world's largest exporter until recently of biofuels. In fact, the U.S. imports biofuel, advanced biofuel from them. So, they have considerable amount of land that is available that is currently in low intensive pasture, livestock production that could be used in the future with more intensive production of livestock and freed up to produce biofuels. And that is all sort of in the southern central part of Brazil, pretty far away from the Amazon. So, without necessarily, causing deforestation directly, and one can argue about what the indirect effects are, but that's, an area where there is significant physical from a land availability perspective and also from the crop perspective. Sugarcane is it's a productive use of land. It is from a carbon intensity perspective, better than corn ethanol. It used to be a much lower cost producer until recently. So that's another promising source. The reason why Brazil has sort of lagged behind the US in part is because Brazil's domestic policies and energy policies are such that they've created a disincentive for biofuel production. And so, in fact, we've had this ironic situation where the U.S. is now exporting biofuels to Brazil, and we're importing some as well. So we're having the circular trade going on in biofuels with Brazil. So that's one region where there is possibility in the future. The other is Africa. So again, large regions in Africa where land is available, where crops like sugarcane and others could be grown in the future.
Right behind you and the front row.
I was just wondering if cellulosic biofuels have the same transportation issues, especially by pipeline, that can be common with ethanol, like the erosion issues?
Yeah, ethanol, once they are produced, the final product is identical, whether you produce it from corn or cellulosic. If it's ethanol, then it has the same problems. You cannot just transport it by regular pipeline because it absorbs water. But, a lot of work is actually going on in trying to produce something called drop-in fuels, which would be exactly like gasoline and not have that problem, and they could be blended without a blend wall. So, and butanol is one example of that. And so really the effort is to bypass this blend wall. And in fact, maybe the answer to the question ahead was that, you could, in fact, bypass the blend wall if you can just produce drop-in fuels. They're very costly to produce right now, but that's another thing sort of on the frontier.
I was wondering a couple of things. One, with the prediction of food shortages and the droughts that we're seeing, can we really afford to put our resources into biofuels? And are we exporting, why are we exporting? I think I've heard that we're exporting them to China as well as to Brazil, and I'm not sure why we're exporting to Brazil if we are getting, doesn't. So a couple of questions about that.
I'll take a stab at
Sure.
that. Maybe we can both answer. I think the answer to your question is no, we can't afford to use corn for ethanol, but that's what we're doing. And we're using, as I said, almost 50% of our acreage in the Corn Belt for fuel. And what scares me when I was talking about going forward is because every year they're increasing this target, and we don't have the types of fuels that Madhu is talking. We don't have these cellulosics yet. They're not available. They can't be purchased, yet the industry is told they must buy them. So that's why we're importing some ethanol from Brazil, because it's truly a low carbon because it's from sugar. And the reason they're importing from us is to replace the exports they send to us. So the ships are literally meeting one another. And you talk about the impact on the environment of that. So you're right on, and it could get worse because of biodiesel. Biodiesel is very inefficient in terms of the use of land. You know, the yields on soybeans are about less than 1/3 of what they are on corn, and you know, only 20% is oil. So even now, the blending of biodiesel is very complicated because it's not cost effective. They're told they must blend up to 10%, but they can't get much past 2.5% because it's too expensive.
What about water? The plan on water resources for biofuels.
Right.
So let me take another, I can get to the water issue, but let me take another viewpoint on this thing and your question of can we afford to do it? And I guess my, you know, just to be provocative, I'd say can we afford not to do it? Because the other thing that, you know, is climate change. So we are concerned about, you know, fossil energy. We have to find an alternative. We are used to, you know, we don't want to, we need to have some transportation fuel, and it has to be, I mean, now we've got a couple different alternatives now in addition to biofuels that are all going to be, you know, that are not without significant challenges, but you could think about using natural gas as an alternative. That's also a fossil fuel, maybe marginally better than gasoline, but again, depletable. The other alternative would be to go for electric cars that have their own challenges in terms of the convenience they provide. So, in some ways, what we really need to, you know, biofuels is a reasonable alternative if we do it right, and if we can move away from food-based biofuels towards these advanced biofuels, and you can actually, with limited land, get a considerable amount of volume that could be used in, you know, potentially. Now it requires, you know, there's sort of considerable technological challenges to it, and having policies that waiver doesn't make that any easier, because it just, you know, there's a lot of investment that goes into it, and then the policy is shaky, and that creates uncertainty and limits incentives for others to invest. So there's no easy solution, but clearly it's not food-based. You know, food-based crops are not going to have, they're not viable, they're not sustainable. But there are other things that could perhaps be sustainable. And from a water perspective, you know, again, you know, the fact that we can grow these in rain-fed conditions means that we don't need irrigation, unlike for corn, where a lot of it is grown with irrigation, and there is that problem as well. There is an issue that these crops do take up a lot of subsurface water, so they don't need irrigation, but they take up what's called this green water, and that, you know, can cause some effects on stream water levels and so on. So you have to be careful how much land is converted in a particular region and which regions are more susceptible than others. So there is some issue of how do you place them in the landscape because of that.
Hi, this question is for Madhu. I was wondering on one of your slides, if I could get a bit more clarity, you had mentioned that there could be an over 100% reduction in greenhouse gas emissions based on the use of certain biofuels, and I was wondering how you calculated that.
So the thing about cellulosic biofuels is that, you know, these are grasses that have a woody outside structure, and then they have this cellulose inside it. And so when you take out the cellulose, you would be left with this thing called lignin, which is the woody stem. And that lignin is a very good, you know, source of feedstock for combustion. So it can be used to generate energy, which would be the energy you need for the conversion process and so on. So unlike corn ethanol, where you have to get natural gas or coal as the energy source in order to do the conversion and to, you know, all the process, here you don't need to do that. In fact, you can, you know, generate extra electricity that could be sold back onto the grid. So that's one reason why the energy consumption is going to be low in these biorefineries. And the other is in the process of producing these feedstocks, they sequester a lot of carbon in the soil because they have very large root systems, they are perennial, so you don't need to be disturbing the soil every year like corn. And therefore you can sequester, you know, 1 to 2 tons of carbon per hectare per year, and can really build up a lot of carbon. There's issues about, you know, that obviously that's not necessarily permanent carbon, because after 15 years, if you dig up that land, you know, that carbon will be released. So there's some questions about, how do you make sure that it remains permanently sequestered? But if you can do that and you count all the benefits you get by replacing grid electricity and the other steps in that process, then the net carbon intensity is actually negative.
I have two questions, but they're totally different, so you can decide whether you want both or not. The first one is regarding the carbon tax. There's a huge push going on in the United States now toward a carbon tax. Seems to be more and more acceptable to both Republican and Democratic theorists. Stephen Jew certainly vouched for it the other day strongly when he was talking at the University of Chicago. And I was shocked and disappointed to see that the carbon tax would do absolutely nothing for what you are proposing here, which sounds so great otherwise. Can you discuss a bit why that is?
Yeah. So the great thing about the carbon tax is that firstly, it would create equal incentives. I mean, in the U.S., if we looked at the ACES Act, which we tried to pass in 2008 or 9, which would have led to a cap-and-trade program in the U.S., would basically have covered the electricity and the transportation sectors, the main energy-intensive sectors. And the carbon tax, just the type of incentives it creates, it would lead to the lowest cost reductions. It would find the cheapest way to make those reductions, and in most cases, those reductions would be made most cheaply by raising the price of coal and gasoline and reducing the consumption of coal and gasoline. And but alternative technologies like the cellulosic biofuels, which may be 2 or 3 times more expensive than gasoline right now, a $50 tax which taxes and adds to the price of gasoline by 50 cents per gallon is not going to be enough to cover that gap between those, and it'll basically people will reduce consumption. It'll not create incentives to buy the high cost but low carbon biofuels. So so the question is, would the carbon tax really be the most effective policy if we want to think long term about transitioning away from fossil fuels? And perhaps the answer is not, because you need to have some alternatives, like maybe if not the renewable fuel standard, but maybe a low carbon fuel standard that really creates those incentives which are needed in the short run to get over the hump of the high cost, till these fuels become cheaper in the long run. I mean, if you look at corn ethanol, 20 years ago, it was very expensive, and it has needed 20 years of subsidies and mandates and all kinds of support. The cost of corn ethanol has come down, dramatically by 50–60%. Till today, I mean, as of today, we are exporting it without any government incentives. It is now competitive with oil. So it's sort of gone through this learning curve, and that's what's led to the reduction. And in order to do that, a carbon tax would not really be enough. I mean, you would never have a carbon tax high enough to be able to do that. The more, in Europe, the price of carbon is 5–10 euros a ton. So, so at least in the short run, one needs to have some of these sector-specific standards that would create those incentives, and then in the long run they could be phased out, and then you can substitute that with sort of. So I mean, ideally, our research would suggest that if you had to have the renewable fuel standard, but if you could couple it with a carbon tax, that would be much better than a renewable fuel standard by itself.
And that, just to clarify, a problem with the renewable fuel standard is you're not getting the consumption reduction that you get with the carbon tax, which is actually something that's highly desirable. So, right?
Right. So if you could combine these, then you get the best of both. You also, in some ways, get the switch towards the better mix of biofuels as well as the consumption reduction together. And so that works much better than either of these policies by itself.
It's a useful caution in thinking about having temporary subsidies for something and then phasing them out is how incredibly hard it is to get rid of subsidies in the U.S., right? So, if the scheme is is predicated on being able to phase out the subsidies. It's something you have to worry about.
The subsidies are supposed to, and all of these things, all of what you talk about just now, which is very helpful, trace back to the fact that you have that huge amount of the price that's tied up in the technology, which I guess isn't very far along right now. Can you talk a little bit about the technologies and how fast it is getting where it needs to go? And that will be my other question.
So the technology is, it's a bit difficult to say. I mean, you know, it's been always sort of, it's not that we don't know how to produce them. We know how to produce these biofuels in the lab at small scales. That you know, the technology for converting cellulose into biofuel is nothing more than the technology used by termites to convert wood into fuel and energy, or the cows to convert grass into fuel. And it's a question of replicating that at scale that is the challenge. And finding the right enzymes that can do this efficiently, that can do this in a continuous process. So one of the issues right now is that, you know, we know how to do it, but we don't know how to produce these cellulosic biofuels in a continuous process. And so, you know, like I was saying, you have the cellulose and you have the lignin, and so you have a start and go process where you have to stop the process, take out the lignin, and then clean it up, then, you know, restart the process. I mean, it's those kinds of technical problems that have not yet been resolved, and that adds to the cost of the capital, which is going to be idle while you do this. The technology is moving forward in that, I mean, in 2014, 2015, there are a lot of companies that are proposing that are going to begin production. I mean, one of the major companies is Poet in Iowa that is going to be producing it from corn cobs and corn stover. So it is moving along, but at a much slower pace than was anticipated. And so it's anybody's guess to say, well, when would we really have that first 1 billion gallons of biofuel that would sort of indicate that we have some kind of a mature process.
Other questions? I'm going to interject a comment, which is that I haven't thought through all the way, which is just that, you know, this building is next door to the Booth School of Business, and if we think that a lot of the problems, the holdups, or concerns about some of the future crops is contracting and management of risk. It's sort of interesting to think about whether or not there actually aren't creative financial instruments that would help the agricultural sector solve that problem. And you might argue that there's a lack of them for other crops because of the existence of crop insurance. I don't know if that's true, but you might argue that. It's not a question, just a comment.
Possibly.
Maybe Wall Street could help. That's all I'm saying.
Right, I guess so. Either help or worsen. I mean, you know, I guess both ways. I'm not sure.
Yeah, no, it's quite possible. Any other thoughts?
So what do we think are the participants of today's discussion?